Welcome back. In example 5, we're asked to find the volume of the solid generated by revolving the region bounded by the following lines and curves about the line y equals 2. So we have y equals x and y equals x squared. Now the key things again to highlight are that we're revolving about an axis. And in this case, it's not the x-axis, it's not the y-axis. We're revolving about this line y equals 2. So this will be, yet again, another little twist in our examples. And here, we're not even given anything, we're not even given a picture. And this is what it'll be like for you. You'll want to be able to sketch the picture by yourself, and then from the picture, it'll help you figure out exactly what you need to do to set up your integral. Okay, so let's first off start with finding the intersection between these two curves. Now, these two curves, you probably should know that they go through 0, 0, and 1, 1. These are our basic line and x squared functions. But if you didn't know that, then you could find the intersection points. And I'm going to leave that to you to work out on paper, and we'll come back and show the work for that. So I'll give you about 5 seconds, not 5 seconds, pause the video, and work out the intersection points and see if we get the same thing. Okay, so you should get 0, 0, and 1, 1. Here's the work to show that. Just set the two functions equal to each other, move all the terms to one side, factor, and then set each factor to 0, and you get x equals 0 and x equals 1. Now, we can use this information to help us draw a picture of our region. So what I'm going to do is draw the coordinate system, and I'll pause the video for a moment to draw it. So there's our coordinate system. I've drawn enough scale to plot these points 0, 0, and 1, 1, and also to have enough room to revolve the region about the line y equals 2. Let me draw in where y equals 2 is, just to put this in here right now for reference. Here's the y equals 2 line that we're going to be spinning our region about. Now we're going to want to draw our region, and here we know that it goes through the points 0, 0 and 1, 1. Both of the curves do. So we have y equals x, which will just be a line connecting those two, y equals x squared, which is going to be a parabola that's going to be going underneath. And there's our region. When we take this region and we rotate it about this y equals 2 line, I'm just going to draw a shadow version of that region on the other side. Oops. There we go. With squiggly lines. Okay, so there's like a shadow copy of it if you rotated it 180 degrees, about, just to get a sense of what this is going to maybe look like. All right, one other thing that we'll do is, as long as we're here, we will label these curves as a reminder of what their formulas are. Okay. Adjust the mic. And now what we can do is think about what the cross sections are going to look like. Remember, when we think about our cross sections, they're going to be perpendicular to the axis of rotation. Whenever we have these revolving a region about an axis, we're going to make our cross sections perpendicular to the axis of rotation so that they look like discs or perhaps washers. Now if we take a little approximate rectangle here, an infinitely thin rectangle at a given x value, so again we're making our rectangles perpendicular to the axis of rotation, right? Always perpendicular to the axis of rotation if you want to use this cross-sectional method where the cross sections are discs or washers. And we're going to imagine what that's like to rotate that about the y equals 2 line. Well, we're going to have this inner circle and this big giant gap that's inside, and then we'll have the actual solid somewhere in between this inner circle and then the outer circle. So the cross-sectional pieces are going to look like these washers. something like those washers right there, with a big gigantic gap in between. Now there's going to be a washer for every single cross-section that's perpendicular to the axis of rotation. Kind of smaller and thinner washers when you look to the right, and kind of wider or more open and also thin washers as you go to the left. The washers get a little bit thicker, at least in this dimension, if you look at kind of in the middle, because the two functions are a little bit farther apart. But when they get closer together, there's going to be like a thinning out kind of effect, where it's going to not be as wide of a washer. There'll be a bigger hole in the middle. All right, so these are what our washers look like. Let's take one of these washers, put it on the page, and we'll start to analyze it. So we'll draw it, let's see, we'll draw it right here. We need to come up with a formula for the area of these washers. So we'll need to find the inner radius, the outer radius, so we can do the area of the outer circle minus the area of the inner circle. Now here we have to think a little bit about what our inner radius is going to look like. Okay, so our inner radius is going to be this vertical distance, and let me just draw that vertical distance. It's going to be this vertical distance right here. That's our inner radius right there. That vertical distance. I should probably, here, let me use the same color as I did down there. So here's our inner radius right here. Now if you think about coming up with a formula for that inner radius, it really depends on the y values. The y value at the top of that inner radius and the y value at the bottom of that inner radius, at least visually for this part right here. Now the y value up here is going to be y equals 2. No matter what cross-section you're looking at, the center of all these cross-sectional washers is going to be at y equals 2. Now the y value down here is going to be tracking along the y equals x curve, right? So we're going to take the y value up on top minus the y value down the bottom here. So that's y equals 2 minus y equals x to get that vertical distance from y equals 2 to y equals x. So the formula for that will just be 2 minus x. It's kind of like the top y value minus the bottom y value. Very similar to 6.1 when you're trying to figure out what the heights of those rectangles are. So we'll have 2 minus x gives us a formula for the inner radius. Okay, so let's look at the outer radius now. For the outer radius, the center of the outer circles is still going to be y equals 2, but now the outside of the outer circle is going to be given by the y equals x squared curve. Right? So if we're going to try to figure out the outer radius, it's going to be the y value up here, which is y equals 2, minus the y value down here, which is given by x squared. So the outer radius will look like 2 minus x squared. Anytime you're finding a vertical distance, you'll always take the top y value minus the bottom y value, so the big y value minus the small y value, in order to get that positive distance, that positive vertical distance. If ever you were trying to find a horizontal distance, you'll take the right x value minus the left x value, because then you'll be taking the big x value minus the small x value to give you a positive horizontal distance. It's the same principle in both cases. Okay, so we have our inner radius, our outer radius. Let's go ahead and find a formula for the area of these washers. And we'll just jump right to it. We'll do pi times the outer radius squared minus pi times the inner radius squared. We can factor out a pi and distribute stuff out just so that we get things out term by term. So distributing the 2 minus x squared out, we get 4 minus 4x squared plus x to the 4th. And then we have a minus from this minus right here. And if we expand all this out, I'm going to put this in parentheses so we remember to distribute that negative in a future step. So we have 4 minus 4x plus x squared. Now we can combine, we can distribute the negative and combine as many like terms as possible, like the 4 minus the 4 will cancel, which is kind of nice. These are gone. And writing the terms in order, you're going to have 4x minus, and then we have a negative 4x squared minus x squared, that's negative 5x squared, plus x to the 4th. So there's a formula for the area of each of those washers. Now we can put that formula into our volume. Our other formula, I suppose, to get the volume. What are we integrating from and to? If you said x equals 0 to x equals 1, that would be correct. Going from the left side of our solid to the right side of our solid. And we'll stick the area of the washers right in there. Now once again, this is a pretty straightforward integral, so you can give it a try and you get 8 pi over 15. All right, so that was a good example of rotating a region about another kind of line, y equals 2 in this case, as opposed to just the x or the y axis. And we had washers going on, so very interesting example. Thanks for watching, and see you in the next one.